1, which is addition and subtraction of whole numbers. Specifically, our focus in Math 1 is on whole numbers. We'll get into other kinds of numbers when you get into Math 2. Some of you are already taking Math 2, but Math 2 kind of takes some of the same ideas from Math 1 and it does it with other types of number systems or a more expanded view of a number system. We're going to be working primarily with whole numbers in chapters 3, 4, and 5. All right, so section 3.1, the first thing we're going to talk about is what we mean by addition. And the idea of addition actually comes back to what we did in the last section of sets, okay? So if we have two just disjoint, that means they don't overlap. Finite, which means they're, we can actually assign a number to how many items are in them, sets. And if n of A means the number of items in A is little letter A, n of B is the number of items in B, then if you talk about A plus B, what this means is it means the number of items in set A plus the number of items in set B. And again, that only works because they're disjoint. They're unconnected to one another. There's no overlap. We call A and B the addends, and we call A plus B the sums. And that language is used in elementary school. So my daughter has brought in things to talk about addends before. So that's a common occurrence even in elementary school. All right, so we're talking about example number 1. It says, give an example to show why in the definition of addition A and B must be disjoint. All right, so what we're going to do is we're going to create sets A and B and make them not disjoint to show that this definition would not work if they weren't disjoint. All right, so let's create a set A with a certain number of items in it. So somebody tell me how many items, tell me what items you want to put in set A. All right, so 1, 2, 3, 4, and 5. This is set A. Matthew started set A, so tell me what you want set B and B then.
Not to be different.
Well, some of it has to overlap with A, but not all of it has to.
4, 5, 6, 7.
Okay, so again, the whole point of this example is to show why we have to have this sort of definitional description that includes the word disjoint. So we've created them to be not disjoint, and we're going to show that this definition doesn't work. All right? So how many items then are there in set A? There are 5. And how many items are there in set B? There are 4. So if I were to create and add together the number of items in B and the number of items in A, how many would I get? There would be 9. Okay, so that's the definition that we've got above. If we were to simply add A and B together, this is what we would get. The problem is that this doesn't actually work. Add in this little piece up here, sorry, I left that out. If we actually calculate the union of this, which is something we learned how to do in the last section. So how many items are in this union? Oh, maybe we should do it this way first. The union. What is the union of those sets? All right, so the numbers 1 through 7. Now, what are the number of items in the union? 7. And the issue is that these aren't equal, aren't they? And according to the definition, they should be. The reason they're not is because why? Right, we created sets A and B that were not disjoint. Because they were not disjoint, they had this overlap when I did my counting, it didn't work out. Okay? And in large part, we saw why this happened in the last section. We had a formula that talked about things overlapping and counting the arguments or pieces of the different circles. And when they overlap, you counted something twice. And in essence, that's what happened when we did this piece right here, the number of A plus the number of B, is we counted what twice? 4 and 5, actually. Yeah, the 4 right here and then the 5 right here got counted twice, which is why I'm exactly too many in my counting, two different descriptions. Okay, so we have to have the items to be disjoint in order to talk about them like this way. Okay. There are several different models for addition. What do I have in here? I have two of them. A couple different kinds of models for addition are the set model and the number line model. So the set model is typically used for whole objects. So when you're counting objects themselves, like crayons. And here's an example. So Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So we're going to draw a picture as we're describing these of what a set model looks like. And you can make your crayons look like whatever you want. I'm going to draw them, in fact, let me use one of these. We'll draw them out sort of as little rectangles. And she has 3 blue crayons. Then here are my, in fact, just for fun, we can make a blue even. Is that? There you go, there's some blue crayons. Some blue. Here we go, there's some blue crayons. What's that? The gradient thing is cool. Yeah, I like it too. All right, so we're gonna have 3 blue crayons. She's got 3 blue crayons, and then she's got, what else? 2 red crayons. All right, so we've got 2 red crayons, 2 red crayons, 2 blue crayons. And what we're going to do is we're going to be combining these together. So if we were to take these, in order to combine them into one conglomerate set of crayons, how many crayons do we have?
5.
We would have 5. And I think I'm going to do it that way. This way. I know it's blue, I'm going to change it. This is a model for addition. It's called the set model. We're actually drawing objects. And you don't have to draw them as rectangles. You could have drawn them as circles. You could draw them as little squares. I don't care what you draw them as, but you're going to draw it. I mean, often they may ask you to draw a diagram of what this is talking about. This is what they're talking about. Because that diagram actually looks like objects that are combined into one group. Okay? A number line model actually looks quite a bit different. So, all right, so a number line model actually is going to have a picture of a number line. Right? So let me draw a line here. So when you're drawing this line, you're actually talking about something that is measured or could be measured in portions. So number line models wouldn't make sense to talk about crayons unless you want to talk about the length of the crayons. And that's not typically what we're talking about when we're doing crayons, right? So things that actually have measurement length, and that's what the issue is. Like maybe you're talking about feet of wood, that's this example, or yeah, feet of wood and feet of aluminum. Maybe you're talking about a measurement of fabric. We've seen some fabric questions in some of the problem solving things we did. So things that you would actually measure would make sense to do with a number line or a measurement model. Right? So when we're taking a look at this one, we're going to start with 0, and we're going to put in here 4 feet of wood. So I've got 1, 2, 3, and 4. So my length of wood is, do it this way. There's my wood right there, the 4-foot long piece of wood. Okay? And then we're going to put it end to end with my piece of aluminum, and my piece of aluminum is how long? So it's 3 longer than the previous one, so this one was 4. This one's going to be 3. And this one's 3. Right, so where does this end? 7. All right, so this is the diagram and the picture that would, oh, now it's up, of course. All right, so this is the picture that we would be representing this kind of a diagram with, this kind of a model with. And just like before, and I didn't write down the answer, we should. So this one's actually going to be 7 feet. And this one would have been 5 crayons. So they have different diagrams, but they also have a different reason for existing, right? So again, I wouldn't use the crayons in the first model because it doesn't make sense to talk about, or at least it doesn't make sense in how we normally think about when I count the number of crayons, right? My son represents or thinks about a blue crayon as this big, right? You know, just a little half crayon. When I ask him to find a blue crayon, he will pick that one just as likely as he will pick the gigantic one, right? Because he just sees them as crayons. But if we're talking about a piece of wood or a piece of aluminum which has measurement or linked to it already, then it makes sense to use a measurement model to do that. All right, definition of less than. All right, so if we have whole numbers A and B, and we talk about A being less than B, we have a symbol for that. You guys have seen it before, the less than symbol. Sometimes students will think about this symbol being as to remember which one's which. There's a couple different ways people think about it. Sometimes you'll hear people talk about that one and say it looks kind of like an L, right? So like an L on its side. Okay. Sometimes you'll also hear people talk about the big part of it, the larger part of it opening towards the larger side. When I was in elementary school or if it was in middle school, I had a teacher describe it as a Pac-Man. Do you guys even know what Pac-Man is? Okay, that's good. So Pac-Man, and it wants to eat the bigger value, so that this is the Pac-Man's mouth. I've also heard people talk about it being like an alligator. What do you have? An alligator. I've heard that used before too. So the larger part of it, or the part of the opening, opens towards the larger side of the inequality is what it is. And this is actually going to be defined to be true if and only if we could add a value to the smaller side that would make them equal. So for example, the reason that 1 is less than 7 is because 1 plus 6 equals 7. There is a number that I can add to 1 and actually make it equal to the other side. That's the definition of what it means to be less than. Okay? So we're going to give an example to a definition of less than using subtraction. So this definition that we've started with is a definition using addition. So to do a definition using subtraction, it's going to look much like this definition. That is, there's going to be words. Like when I say explain, those words, same thing here. Okay. So we're going to say, for any whole numbers, A and B, and instead of us defining about less than, instead of us defining it in terms of this less than symbol being addition, we're going to do the same thing on less than, but we're going to define it in terms of subtraction. So A and, I didn't get my B written today. A and B. A is less than B. Written A and symbol less than B. If and only if there exists a natural number K such that what? Say it louder for me. All right, and so I'm going to keep the order the same with the A on the left, but I'm going to do what you said. I'm going to take the K and I'm going to subtract it from the B instead of adding it to the A. This isn't really any different, right? But we're defining it with subtraction instead of defining it with addition, which is what we're asked to do. And I can create this again and talk about this. 1 is less than 7 because 1 equals what? 7 minus 6. Right? That's why 1 is less than 7, is because there's a number that I can take away from 7 to get back to 1. So it's a different way to think about it, but it's the same. It's basically the same idea. And we're going to take a look at 4 properties of addition. Can I switch this slide? Okay. All right. 2, you're going to see these again in Math 2. You have taken Math 2, and this is the second time at least for each of the families. And I know that you've seen some of them before because they are introduced in elementary school. Okay? So some of them are ones that you forget which one they mean, and others of them you tend to remember more. All right, the first one is called the closure property. So here's what I want you to imagine. I want you to imagine all of these numbers floating around in the air. Can you see them? Here's the number 1, it's over here, floating around, and number 3, maybe it's back there by Anna, up here by Lydia's number 4. They're all floating in the air. Okay, all these numbers, they're all whole numbers, because we're talking about whole numbers in this section. So whole numbers, remember, are 0 and up. The counting numbers from 0, 1, 2, 3, and up. Okay, so these are all whole numbers. So if A and B are whole numbers, then A plus B is a whole number. Okay, so all the whole numbers are floating around in this room, and that door to the room, we have to decide if it's opened or closed. If I can take these two numbers, whatever they are, as whole numbers, and I can add them together, and I get another whole number, that is another number that's floating around in the room, then it means the door is closed. And that happens for addition and whole numbers, right? If I add 1 plus 7, I get 8. Is 8 a whole number? Yes, so it would also be in this room. I don't have to go outside the hall to catch that number. And you might think, well, yeah, duh, does that not work all the time? And the answer is actually no, it doesn't. So let me give you a couple of examples of ways that that fails. But in order for it to fail, I have to go either outside of the whole numbers, because that's what I'm working with, or I have to use something that's not addition, which is also what I'm working with. So I'm going to give you one of both of those ways that you can think about this failing. The easiest way to fail is to talk about something that's not whole numbers, okay? So let's talk about the easiest, to talk about the way that it fails if you don't talk about whole numbers. Let's say that we're working with something that's decimals, okay? Specifically decimals, I don't mean, you know, a decimal like 3.1 or 3.0. I don't mean like that, I mean a legitimate decimal, okay, like 3.1. So if I add 3.1 and 1.9 together, what happens? So if all I have floating around in this room is legitimate decimals, what I mean by saying there's something after the decimal point that's not a 0, and I add two of those numbers together, I don't always get that same kind of number again, do I? So that would be a non-closed set, because I would have to open the door, go out in the hallway, and find the number 5, because it wasn't a decimal point number. Does that make sense? Because that's one way for it to fail. That's a good question.
Yeah, I just was going to ask you
So if you add 3 point, I was giving some examples of numbers. If you add 3.1 and 1.9 together, what do you get? You get 5, which does not have a decimal point. It's not a 0. This is a number after the decimal point, 0. What we have. And if the room were containing only numbers that had the decimal points, then I would actually have to open the door to find that number out in the hallway or downstairs or whatever. That means that door would have had to have been open therefore it wasn't closed. Subtraction is easy to do this with too. I can use whole numbers to subtract. So let's say, what if I had, well, one thing I can do is do something like 7 minus 3. What's 7 minus 3? 4. It's a whole number. No problem, right? What if I do 3 minus 7? I get a negative. And negative numbers are not whole numbers, right? Which means I had to open the door, go out in the hallway, and find negative 4. This room had only whole numbers in it, so that set with subtraction, whole numbers with subtraction, would not be closed. Okay, is everybody with me on that? All right. Next one, commutative property. The commutative property says the following. If you have whole numbers A and B, then A plus B equals B plus A. The commutative property means you can do it in the reverse order. Do something in the reverse order. Okay, so again, this is a commutative property with addition for whole numbers. The addition is the key idea. Because if I do this with subtraction, what happens? It's not the same, is it? In fact, I just gave you an example of that a minute ago. 7 minus 4 and 4, or 7 minus 3 and 3 minus 7, right? If I do the subtraction in the other order, it changes the value. So this is very specific to addition.
What
Yes.
time did they start teaching? You know?
The idea of them being reversible, probably about second grade, I think, is when I saw things coming home from my daughter's class. Yes, and I've heard her use the word commutative before too, just so you know.
And she gets it.
Yeah, just that. Yeah, I mean, they don't formally keep talking about it in the same way we are going to talk about it in here, but she does get the idea that the order doesn't matter, which is the key idea for commutative, right? That the order doesn't matter. Associative. All right, so associative, if I do A plus B, and then I add C to it on the end, this is the same thing as doing A, and then, oops, I'm sorry, left my plus sign on. Let's try again. A plus, and having done the B plus C first. Okay, so associative is who you're associated with. Okay, so if you talk about your associates, the people that you know or that you talk to or whatever. Associative property, you see parentheses. The parentheses changes who they're associated with. So on the left-hand side, A and B are associated because they're in a set of parentheses. On the right-hand side, the B and the C are associated because they're in a set of parentheses. Okay? So what this is telling you, again, is with addition, it doesn't matter how you do the associations, you end up with the same result. And you guys know this because you've done this before with just flat-out numbers. You've done it in algebra as well, where you regroup things with the terms that are alike. So in algebra, you would have seen something perhaps like x and then plus and then 3 plus x over here. Well, you can't add the 3 and the x together because they're not like terms. So you move things around and you redo where the parentheses are located so that you combine the terms that are alike. It's also a really helpful tool to have if the addition doesn't happen to be in a nice way. For instance, let's say that you had something like that. That's not the best example. How about I do 18 here? Okay, so depending on how you group these together will depend on whether the addition is easier than others. I don't know about you, but I would rather add 72 and 18 together than 72 and 34 or 34 and 18. Any idea why? Because the 2 and the 8 make 10, right? So I could actually use two properties here. So if this had started out, for instance, like this, one property is I can move where my parentheses are located. I can change them. The other property is I can actually switch numbers orders. So I actually would want to remove the parentheses, switch the 34 and the 18, and then insert the parentheses back at the beginning. And I'm allowed to do all of those things because I've got the commutative property, which says I can switch the order of things. And I've got the associative property, which says I can switch which things are grouped together. But again, all of this works because it's addition. If you do this with subtraction, it's going to fail. It's not going to work at all. You're going to get things happening not what you wanted. Right? Our last one, the additive identity property. So there is a unique whole number 0. 0 is your best friend. And 0 has the property that when you add it to anything, what happens? What happens? It's itself, whatever you started with, right? And in fact, it doesn't matter where you add it, if you add it before or afterwards. Either way, you end up with the value you started with. The identity doesn't change the value you're working with. And you use this property, right, when you get to algebra, because you do things like adding a value to both sides of an equation, right? You do this kind of thing. Where in essence, you've really added nothing because you've done it on both sides of an equal sign. It's partly using that property. You also see this in higher levels of algebra when you add and subtract a value to the same side of the equation. I'm thinking in particular of doing things with completing a square. If you remember that vaguely, algebra 2 kind of stuff. So you're using that idea much later on, but we talk about this idea very early. You know, the fact that if you add something to 0, it doesn't change its value. All right. So what we're going to do on the next slide is we're going to actually identify which property is being used in which example. So on the first one, this says 6 plus 8 is equal to 8 plus 6. What property is that? That is commutative property, right? Because the commutative property says I can do it in the reverse order and it doesn't change the result. Now, B, C, and D all have parentheses. That does not mean that they are all associative. So first of all, get that out of your head that parentheses means that this being associative. You need to figure out what the parentheses are doing. So on part B, it says 6 plus 3 in parentheses plus 0 equals 6 plus 3. What property is used there? That is the identity property, right? The parentheses had nothing to do with what associative parentheses do for us. This is the identity property. And it wouldn't hurt if you wanted to get in the habit of writing additive identity, because we're very quickly going to find multiplicative identity in the next section. I think it's in 3.3. So if you want to write additive identity, that would be great. At this point, it's the only identity we talked about, so if you just write identity, it's okay. How about this one down here, part C? Okay, so Heather says it's commutative. Why, Heather?
Because all it does is switch the 6 and
Right. So it actually still has the same numbers inside each parenthesis, right? But what switched was the order of the numbers that were inside, and that's a commutative property. So this is maybe an odd way or a way that you haven't thought about seeing it, but this is the commutative property. How about the last one? That is associative, right? Because the parentheses here are around the 5 and the 3 on the left, but the parentheses on the right are actually around the 3 and the 2. This finally, with the parentheses, is the associative property. All right, I actually already did an example of this. It wasn't a whole example, but we mentioned it in passing. There are some basic counting strategies or basic addition strategies we're going to take a look at. We're going to look at some basic multiplication strategies and some subtraction and division and things too. So we're going to start with some basic addition strategies. And some of these are used more than others, and some of them are used in different contexts than others. It just kind of depends a little bit on the numbers that you're working with. So the first counting strategy, or the first addition strategy, is counting. So it's starting with the lower value and counting up. Have you done that before? Yeah. So if it said something like, we'll do an example. I'll have you written down so we'll see how I can pick it up. If you had 5 plus 8, I didn't think you needed to start necessarily with the lower value, but you start with one value and count up from there. So you start with 8, and this is what I do, right? You do 8, then you go 9, 10, 11, 12, 13 on your hand, right? And once your hand says the other number, then you're done, and that's actually going to be your answer, 13. So you're starting with one or the other. It doesn't actually have to be the lower value, and you're counting up to the one that you were starting, that you actually had left, that you didn't have to start with, the other one. Doubles. If a student knows doubles, and they do teach doubles, they can think about, for instance, 3 plus 4 as double of 3 and add one more. I don't particularly find this a very useful strategy, but it is something that is taught. My daughter talked about doubles, and she talked about things also called near doubles. You heard that phrase before? 3 plus 4 would be considered near doubles, because they are nearly double the other value. So you'll see this sometimes too, where you're taking a value and you're switching it a little bit up so that it makes it a double that you remember. Okay. Making 10. This is one that I mentioned just a little bit ago. Mackenzie and I were talking, right? When you saw the one that, or not Mackenzie, it was actually Jordan, said, oh, I would add this together. Was it Jordan? No, it was Mackenzie. It was right the first time. Where you saw that and you said, oh, I would like these numbers to add together because the 8 and the 2 make a 10. Okay. So this is the idea of making a 10. All right. So a method for adding to a value of 10, including the leftovers. For instance, thinking about 8 plus 6 as 8 plus 2, and then add the other 4 afterwards. Okay. These are a simple, very simplified example, but that would be an idea. Another idea is to do a counting back idea. Okay. Much like the counting on idea, counting back is an addition, actually a subtraction strategy, but it's included in the same section of strategies that we're taking a look at. All right, let's take a look at another one. So specifically, some subtraction stuff now. That last one led us into it. All right, so subtraction of whole numbers says that if you have any whole numbers A and B, and A is larger than B, and we need A to be larger, otherwise we're not going to be in the whole numbers when we subtract. So that's why that condition is actually there. As long as A is larger than B, then when we talk about A minus B, we actually get another whole number C. And that number C is the difference between the two. In other words, it's the value that we would have to add to B to get back to A. There are 4 different models for subtraction that we're going to look at. So the first one, and you have to get out of your mindset about what subtraction means. Subtraction means that definition in blue at the very top. That's what it means. Some of you probably think about subtraction in one of these 4 ways and think that is the definition of subtraction, but it's actually a model for subtraction. It's one of the ways we think about subtraction. So here's the first one. Model subtraction, takeaway model. Abby had 24 rocks. Eli sneaked into her room and took 5 of the rocks. How many rocks does Abby have now? All right, so what we're going to do is we're going to do a picture of our rocks, and I probably should have stuck with a smaller number. How about I switch it? Can I change my 24 to 14 so I don't have to draw so many? You guys okay with that? Okay, let's make it 14 rocks. All right, so I'm going to draw some rocks. You are too. Your rocks will probably draw much faster than mine. So I have 14 rocks. So the idea of this, or the image of this, is that I've got these 14 rocks in a set, and Eli sneaks into the room and he steals them. Sounds like something a little brother would do, right? All right, so he sneaks in, he takes away 5 rocks. So we're going to remove 5 of these rocks out of the picture. They're no longer in there. And the question is then, if I took them away, how many are left? And how many are left? 9. Okay, there's 9 rocks left. We've all heard of a takeaway model before, right? This is typically what you learn first. If I asked you what subtraction is, probably 15 or 16 of you would have told me it's takeaway. If I have something in a removing part of it, that's what subtraction is. Okay. Missing addend is another model. Missing addend is the idea that I have something that I don't have enough to do whatever I need to do with it. Right? Missing addend would be the idea that you need $5 to go eat lunch at wherever, but you only have $3 in your wallet. That's a missing addend idea of subtraction. So here's an example. Eli needs to collect 10 leaves for a school project. He and Abby go out and find 8 leaves. How many more leaves does Eli need? Now I need to show you what the picture looks like for this, because the picture looks a little bit different, the diagram for what this looks like. He has how many?
7.
He needs 10. How many does he have?
8.
He has 8. So I'm actually going to show that I have 8 of these items. Okay, so he has 8 of them, but he needs 10 of them. So what we do to draw this is we actually draw in the 2 that are missing on it's some kind of a dotted diagram. It's the missing piece, sort of like a placeholder for what's not there. Okay? You also see this done as an introduction, and then of course what goes in this piece, what's missing. I should have drawn it quite like that. Let me fix that. What's missing in this piece right here is 2 of these guys. Right? That's the pieces that are missing. Here's how you see this used a lot. Okay? You see this used a lot in something like this. Here's any equations like that. There's a blank spot. That's a missing addend equation, I guess you would say. The things that we see a lot right now in mathematics is the idea that we want to get kids, and you too, away from the idea that equal means find the answer. Because you see, the answer in this one is not after the equal sign, is it? It's actually the missing blank spot. So equals does not mean find the answer. Equals in this case would mean balancing something. What's missing in the box that makes this balance, that makes both sides the same. So you see this actually written in an equation form a lot of times as well. This is also sort of what we see being moved into for algebra now. Because in algebra, the idea where you see equals and people think that means find the answer is very distracting. Because that's not what happens when you get to algebra. Equals does not mean find the answer. And unfortunately, in elementary school, sort of historically, it has meant that. Equals means this is the answer comes next. The answer is next after this piece. And so we've got this sort of blank spot to help us get away from that idea that equals means finding the answer. All right, comparison model. All right, Jessica and Jeremy play basketball. Jessica scores 12 points. Jeremy scores 8 points. How many more points did Jessica score than Jeremy? So in this case, you're not taking anything away and there's nothing missing. Do you see the difference? So the kicker here is that we're actually comparing. It's still a subtraction problem, agreed? But it's with a very different mindset than it was before. I don't have something and I'm removing something, and I don't have something that's missing. Now I could change the question so that it asks it in a different way, but the problem as it's set up right now is comparing two different things. So what I'm going to do is I'm going to compare them, and we'll just draw them as points with hash marks. Okay, how long do you do hash marks with a number? So we're going to do 12 points. So here's Jessica. She has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then we're going to put Jeremy underneath. And what we want to do is we want to draw this in such a way that things line up and I can see exactly, again, from a picture point of view, what is missing, if you will, when I compare them. So Jeremy has 8 points. So I'm going to line them up exactly underneath the points that Jessica has. But I've only got 8 of them. I think that's 8. So the answer then is the piece right here that is missing when I sort of compare 1 to 1, this top line and the second line. And you see how many more did Jessica have? 4. There are 4 more here. Still subtracting, but for a very different reason on this problem. All right, the last one of the models is the number line model. Now, we've seen a number line model for addition, and this is a very similar idea for subtraction. Again, we see this number line measurement model used when we're measuring something. Okay, so again, I wouldn't talk about the number of points in basketball because you can't have half of a point. It doesn't make any sense to use a number line model to measure this. Okay? But in this case, on this problem, you see miles. Okay, number of miles, in this case, to the mall. So Luke drives 15 miles to the mall. He's on his way home. His mom called to ask where he is. He states he's coming home, and he's now 8 miles from the mall. How far is Luke from home? So we're going to draw a model, a line. And our line, the full distance is going to be how far? 15, because that's how far away the mall is. So here's 0, and I'm going to mark out until I get to 15. All right, so the full distance that Luke has gone is, we'll use some different ones. He's gone right here, right? From here to the mall, 15 miles, that's how far. But Luke's now going to turn around. So if you imagine, for instance, you can actually write this in if you'd like. This is home, and this is mall. He's gone part of the way home. How far has he gone home? How far? Is it 8? 1, 2, 3, 4, 5, 6, 7, 8 from the mall. Whoops, there's the wrong number. Okay, from the mall, he's gone 8 miles. So he's gone from here all the way back over to there. This is 8 miles. And the question is then, how far does he still have to go? How far is he going to get home? 7. So he ends up being 7 miles farther from home still, or 7 miles away from home still. This is a measurement for a number line model. All right, I'm going to pause right here.